Select the major product of the following reaction. So we have a substituted benzene ring, and we're treating this to EAS bromination, electrophilic aromatic substitution bromination conditions. So these are the conditions to replace one of the hydrogens on this starting material with a bromine. So in order to decide where that bromine is going to be added to the ring, we need to know what sort of director this group is. And so we have an alkyl group here. So that is a carbon-based group, and these are orthopara directors. And we can see that in the way that they can stabilize the carbocation intermediate that forms in an EAS reaction. And so this will direct an incoming bromine to the ortho or the para positions. In this case, we have a tert-butyl group. This is really quite large in terms of steric hindrance. And that steric hindrance is going to block these ortho positions. The ring is flat, which means that this substituent and anything you're adding to the ortho positions will be lying in exactly the same plane. So as soon as you get a lot of branching, that's really going to block those adjacent positions. So we're mostly going to have the bromine add to the para position. So that is option D. So we've answered the question, but I'd like to take the time to go through and draw this bromination mechanism. So your benzene ring is not going to react as readily with molecular bromine as something like an alkene. So we often need an extra catalyst like iron tribromide. You might also see aluminum catalysts used as well. So the first thing that happens is that the bromine is going to react with that iron tribromide catalyst to make a really good electrophile that's capable of reacting with the benzene ring. So the first step is just a Lewis acid base reaction between the molecular bromine and that Lewis acid catalyst. And so this is giving you what is going to be the really good electrophile in this reaction. And so we've attached this molecular bromine to the iron. So the iron now has a negative charge. This central bromine that has two bonds has a positive charge. And now we've made a really good electrophile. So we're going to show this tert-butyl benzene reacting with this really good electrophile. And so because we've identified the major product as the para product, I'm going to use the bond here as the nucleophile because that'll allow me to attach the bromine to that para position. So this is going to attack the N-bromine and break this bond, giving us a carbocation intermediate. So we've got the tert-butyl group on here, and here is the carbocation intermediate that we have formed. And we saw in a previous video that this alkyl group directs to the ortho and para positions because when you have the electrophile add to either para or ortho, you can draw a resonance structure, you just move this bond down, that would put a positive charge exactly where it could be stabilized by that alkyl group. So that's why this is an ortho-para director. To get to the product, which is here in D, we just need to remove this hydrogen. So you're always removing the hydrogen at the same carbon where you added the electrophile. So that's how you are doing the substitution. So you're adding and then taking off the hydrogen. And so the base that we'd have in this solution would be this iron tetrabromide, which is an anion. And so we formed it right here when we broke this bond. And so the way that this is going to react is we're going to take the electrons from this iron-bromine bond. So this is going to regenerate FeBr3, which is our catalyst. And it's also going to generate as a byproduct HBr. So these electrons are coming in here. So that's going to form this para-substituted product. You're also going to form some HBr. We see that forming right here. And you're also going to regenerate that iron tribromide catalyst so that you can continue the reaction.